Usually when we talk about a physical workspace, there's this underlying assumption that if your desk is messy, your mind is messy.
Oh, yeah, 100%.
Right. Like you spend half your time just looking for a specific pen or shuffling through stacks of completely unorganized paper. By the time you actually start doing any real work, you're completely exhausted.
Yeah, exactly. I mean, the overhead of just managing that chaotic environment completely gets in the way of executing the actual task.
Yeah.
You're drained before you begin.
And that is exactly what we're looking at today in this deep dive, because we have a set of developer logs from 2026 by someone going by the handle Luck036, and they're dealing with this exact problem of a messy workspace, but, in the context of a microchip routing algorithm.
Right, which is fascinating. Because when you step into the world of software architecture and memory management, a disorganized workspace isn't just a minor inconvenience. It's not just annoying.
No, what's a huge deal?
Exactly. It is a fundamental roadblock
Mm.
that can literally bring an incredibly complex system to a grinding halt.
Yeah, and we are looking at the absolute definition of a structural bottleneck here. So the specific system in these logs is called a DME algorithm, which stands for Deferred Merge Embedding. And to give you some context on why this matters, DME is used in physical design routing for microchips.
Right. And just imagine a modern processor with, billions of transistors. I mean, they all need to march to the beat of the exact same drum, which is the clock signal.
Like a conductor in a massive orchestra, right?
Yeah.
Just making sure the violin and the tuba play their notes at the exact same millisecond.
Precisely, yeah. Because if one electrical signal arrives even a fraction of a nanosecond too late, maybe because its wire was just a tiny bit too long, the entire chip can fail.
Which is crazy to think about.
It is. So this DME algorithm is basically responsible for figuring out the perfect physical geometry of the wires to ensure those perfectly synchronized arrival times.
But the algorithm in these specific logs was really dragging its feet. I mean, it was incredibly slow. And the developer realized the solution wasn't just, a minor code tweak.
Right. They couldn't just change one line of math to make it run faster.
Exactly. It required a complete teardown and a fundamental shift in how the system organized its memory.
Okay, so let's unpack this a bit, because the core issue was the data structure itself, which is essentially this massive branching tree of wire connections. And in the original C++ code base, they managed this tree using something called a standard shared pointer.
Okay, so for those of us who aren't dreaming in C++ memory allocation rules, what does a shared pointer actually do? Like, why is that bad?
Well, think of it using that physical workspace analogy you mentioned. Imagine you're trying to read a single highly technical book,
Okay, got it.
but instead of being bound together, the pages of this book are just scattered randomly across different floors, different rooms, and different shelves of a massive library.
Oh, wow. That sounds awful.
It is. And that chaotic, scattered storage space is basically what programmers call the heap.
Oh, I see. So to read the book, every time you finish page 1, you have to look at this little index card at the bottom that tells you where page 2 is hidden.
Exactly.
And then you have to walk up 3 flights of stairs, find the specific room, locate the shelf, and grab the next page just to read one page.
Right. And that walking time is your computer's processor essentially doing nothing. I mean, it's just sitting there waiting to fetch the next piece of scattered data.
That is so inefficient.
But wait, it gets worse. Because it is a shared pointer, it introduces something called reference counting overhead.
Okay, what does that mean? Like the library has an incredibly strict administration policy or something.
That's a great way to put it. Yeah, every single time you look at a page, you have to sign a logbook saying, I am currently looking at page 42.
I get it. And when you put it back, you have to sign out saying, I'm no longer looking at page 42.
Exactly. Because the computer has to constantly increment and decrement these little counters to ensure no one deletes a page while someone else is actively reading it.
So you end up spending way more computing power doing library administration and walking up and down stairs than you do actually processing the data.
Exactly. It is terrible for the processor's cache.
Yeah.
The computer's ultra-fast, short-term memory, it desperately wants related things to be located right next to each other.
Right. So the messy desk is literally destroying the workflow.
Yeah.
And beyond just being slow, I was reading that this old system created a massive logistical nightmare if you wanted to edit the book.
Oh, absolutely.
Like, the rules of those shared pointers made it incredibly difficult to safely edit 2 different pages at the exact same time.
Which is a huge problem. I mean, it's a severe limitation when you're building an efficient algorithm that needs to constantly update multiple branches of a wire tree simultaneously.
So, to fix this whole mess, the developer just threw out the scattered library system entirely. They moved to an architecture called an arena, or an arena-based tree.
Right.
And in the logs, this is represented as moving everything into a single vector. Now, a vector in non-programmer terms, that's just a rigid sequential list, right? Like item 2 is always physically glued right next to item 1.
That is exactly it.
Mm.
Instead of the pages being scattered all over the library, they are printed and perfectly bound into a single contiguous notebook.
Oh, nice.
Everything is strictly sequential. And instead of complex pointers requiring you to follow some crazy treasure map to find the next node, you just use simple indices, page 1, page 2, page 3.
So no more walking up and down stairs. No more signing logbooks.
Right. And if we connect this to the bigger picture, the performance implications of this shift are massive. First of all, it completely eliminates what we call allocation overhead.
Meaning what exactly?
Well, when the computer needs to add a new connection to the tree, it doesn't have to scan the massive, messy library for empty shelf anymore. It just flips to the next blank page at the end of the notebook and writes it down.
Just boom, done. Zero allocation overhead. Okay, but what about that editing problem we talked about earlier, where the old scattered system kind of locked you out of updating 2 branches of the wire tree simultaneously? Does putting everything into a single notebook actually solve that?
This is where the arena concept really shines, especially when the developer started working in Rust.
Right, because Rust is super strict.
Extremely strict. It has incredibly strict rules about memory safety. But because everything's indexed in one clear, contiguous array now, the developer could utilize a feature that grabs a mutable pair of variables. It's called getPairMut.
Okay, get pair mut. How does that work?
Essentially, the system can look at index A and index B and prove to the computer, hey, I know for an absolute fact these are 2 distinct, separate pages in the notebook.
Oh, I see.
Yeah, so it says, therefore, it's completely safe to edit both of them at the exact same time without them interfering with each other.
Wow, that is such a clean, elegant solution. You fix the physical layout of the computer's memory and suddenly all the administrative bottlenecks just vanish.
Exactly.
But, fixing the memory layout is really only half the battle here. Because once you speed up how fast you can fetch the data, you inevitably expose the flaws in the actual math being done on that data.
That's right. The bottleneck shifts from memory access to the computation itself. So now that we have this lightning fast access to our tree of wires, we have to efficiently calculate the tapping points.
Right, the tapping point, which is the exact physical spot on a microchip where 2 branches of wires merge together into one.
Exactly. And in the original version of this algorithm, the code calculating that connection point did something inherently risky.
What did it do?
Well, it calculated the math for the connection, but as a side effect of doing that math, it simultaneously mutated the tree.
It altered the data structure while figuring out the answer.
Yes, it was changing the actual data structure in the background while it was doing the math.
Okay, wait, I have to push back on this for a second. We are talking about microchip design, right? An industry that is utterly obsessed with speed and efficiency. So if the old algorithm calculated the connection point and built it right then and there, isn't that just killing 2 birds with 1 stone? Like, why is it considered a flaw to do the math and apply the change at the same time? It seems like splitting those steps up would just slow the software down.
Yeah, I mean, it is a valid point.
Yeah.
And intuitively, doing 2 things at once seems faster. But in complex systems architecture, coupling computation with mutation creates what programmers call side effects.
Side effects, okay.
And it becomes an absolute nightmare to test, debug, or reuse that piece of code. Think about it like hiring an architect to calculate the square footage of your living room.
Okay, I'm with you.
You ask them for the measurement, right? But while they're walking around with their tape measure, they secretly knock down a wall and move your sofa because their calculations suggested it would optimize the space.
Oh, wow. Yeah, I see what you mean. I just wanted the number. I didn't authorize a remodel.
Exactly. The unpredictability is the issue. Because if the algorithm fails later on, you don't know if the math was wrong or if the hidden wall smashing caused a structural collapse.
That makes total sense.
So this is why the developer shifted to a pure function approach. They basically separate the architects from the construction crew.
So the pure function just observes.
Exactly. It takes in the data, it performs the complex math, and it returns a clean, highly detailed blueprint called a tapping result.
Got it.
It doesn't touch the tree. It doesn't move any walls. It just hands the calling program the blueprint and says, here is where the math says the connection should happen. It is up to you to actually build it.
Wow. That separation of concerns makes testing incredibly straightforward, doesn't it? Like you can throw 1,000 fake living rooms at the architect and verify if their tape measure works without actually building anything.
That's exactly the benefit. And this pure function approach is where the developers started utilizing different ways to calculate the delay of the electrical signal. The logs mentioned moving from a linear delay model to an Elmore delay model.
Oh, let's unpack the difference there, because I imagine the math gets significantly heavier.
Very much so, yeah. So the linear model is basically high school physics. It assumes the microchip wire is a perfect frictionless vacuum.
Okay.
So it calculates delay purely based on distance. If the wire is twice as long, the signal takes twice as long. Simple.
But a microchip isn't a frictionless vacuum. I mean, it's real physical metal.
Right, which is why the pure function needs to handle the Elmore delay model, because Elmore actually accounts for the messy physical reality of electricity.
Like what kind of reality?
Well, it factors in resistance,
Yeah.
so the friction of the wire itself, and capacitance, which is essentially the wire storing up electrical charge and slowing the signal down.
That sounds complicated.
It is. The math required to calculate a merge point using Elmore is vastly more complex,
Yeah.
which makes having a pure isolated function to handle it even more critical.
And when this pure function finishes battling all that complex physics, it returns that tapping result blueprint. But, there's a detail in the developer logs here that is absolutely fascinating to me. Inside that blueprint, the pure function includes something called a raw value.
Ah, yes. This is where we transition from purely software architecture into the physical geometry of the chip itself.
Right, because the pure function spits out a raw value for where the tapping point should be on a specific segment of wire. But sometimes, mathematically, the ideal connection point falls completely outside the physical bounds of the wire.
Exactly. Let's say we have a wire segment connecting 2 points and it is exactly 10 units long.
Okay, 10 units.
The pure function runs the Elmore physics math, and it says the perfect synchronized merge point is at -4.
Wait, -4, which physically makes no sense.
Yeah.
The wire starts at 0. You cannot connect a new wire to a point in space that is 4 units behind the start of the existing wire.
Right, you just can't. So the algorithm has to obey reality. It clamps the connection point.
Meaning it snaps it to the closest real point.
Yes. If the raw value is negative, it snaps the physical merge point to 0. And if the raw value is greater than the distance, say 14 on our 10-unit wire, it snaps it to the maximum distance, which is 10.
So it anchors the blueprint to the physical grid. But here's the secret sauce that I found so cool. The algorithm clamps the value for the actual physical connection, but it explicitly preserves that impossible raw value inside the blueprint.
That's right.
It doesn't throw the -4 away, it hands it back to the caller.
It intentionally keeps the mathematical error.
And the reason why is literally the key to solving the hardest problem in the entire routing system. Because how do you deal with an impossible negative number? You use it to dictate elongation.
Exactly. Which raises an important question. What exactly is elongation in physical design, and why is it necessary?
Okay, here's where it gets really interesting. So the whole point of the clock tree is perfect synchronization, right? But you constantly have imbalanced delays.
Right.
You have one electrical signal racing down a highly efficient wire, arriving way faster than a signal struggling down a complex resistant branch. They are totally out of sync.
You have a fast side and a slow side.
Exactly. Think of it like a bustling airport security checkpoint. You have a lane with fast prepared travelers and a lane where people are moving incredibly slowly, taking their shoes off.
Oh, I know that feeling.
Right. If your goal is for everyone to reach the screening desks at the exact same synchronized pace, what do? You can't suddenly make the slow lane move faster.
So you have to artificially slow down the fast lane.
Yes. You build those convoluted zigzagging rope lines. You don't ask the fast people to walk at a slower pace. You force them to walk a much longer, winding physical distance.
That is a great analogy.
They cover more ground, taking up more time, so they arrive at the desk at the exact same moment as the slow lane. And in microchip design, that zigzag rope line is called elongation.
And how do we know exactly how long that zigzag needs to be? We look at that preserved raw value.
Oh, right. The -4.
Yes, exactly. Let's walk through the mechanics the developer outlined. So we have our wire with a distance of 10, the fast signals coming from the right, the slows on the left. The pure math told us the ideal merge point is at -4.
The mathematically impossible point past the slow side.
Right. So the system clamps the physical merge to the left node to 0. The The left wire length basically becomes 0 because the connection is happening exactly at its location.
Okay.
But the math dictates that the right wire, the fast wire, becomes the original distance minus the raw value,
Wait, so 10 minus -4.
which equals 14.
Oh, wow. So a wire that is physically bridging a gap of only 10 units is now mandated by the software to be 14 units long.
And this is where the physical layout actually adapts. Because a microchip operates on a strict grid, the wire can't just stretch out into empty space, and it can't run diagonally.
Right, there are physical constraints.
So it takes what engineers call a Manhattan path.
Manhattan Pat, like navigating the grid of city blocks in Manhattan.
Exactly. It physically snakes on the grid. It writes up, over, down, and over, intentionally taking a highly inefficient, longer route just to add physical wire.
That is brilliant.
It uses those extra 4 units of length to add resistance and capacitance, intentionally delaying the fast signal so it perfectly synchronizes with the slow signal.
So the math gave us a negative number, and instead of throwing it out as just an error, the developer realized it was a precise prescription. The raw value is the exact length of the zigzag required to balance the system.
And the logic perfectly mirrors itself on the other side, too. If the raw value is 14 on a 10-unit wire, it clanks to the right side, the right wire becomes 0, and the left wire snakes out to 14 units.
That is so cool.
Yet preserving that out-of-bounds data in the pure function blueprint is exactly what makes caller side elongation physically possible.
Okay, so we have this incredibly elegant theory. We've organized our memory into a single contiguous arena notebook to eliminate overhead.
Check.
We've isolated our math into testable pure functions so they don't smash hidden walls. And we are using those impossible raw values to build zigzagging wires to perfectly sync our electrical signals. I mean, it sounds brilliant on paper, but, theory is cheap.
It really is. The ultimate test of any architectural overhaul is whether it actually routes a chip successfully without breaking 1,000 other dependencies.
And the developer didn't leave that to chance. The logs detail a massive verification process where they took this entire architecture, originally built in C++ as FISDs, CPP, and painstakingly translated it directly into Rust as FISDs.
Which is a huge undertaking. Porting a complex algorithm involving physical modeling across 2 languages with vastly different memory paradigms is an incredible friction test.
Because they handle things so differently.
Oh, totally. C++ trusts the programmer implicitly, while Rust violently rejects anything that isn't provably safe.
And the testing volume reflects that friction, too. They logged 149 rigorous tests in the C++ version, featuring hundreds of assertions.
Right.
And when they ported it to Rust, they actually expanded that to 346 tests.
Because the goal here isn't just to make sure the code compiles. The goal is numerical parity.
Meaning what exactly? Like the answers have to be identical.
Yes. Meaning the Rust pure functions, calculating that messy Elmore physics, evaluating the tapping points, and generating the elongation snake lengths produce the exact same mathematical outputs to the decimal point as the C++ original.
Wow. Achieving that level of cross-language consistency is kind of the holy grail, isn't it?
It absolutely is. It proves that the architecture isn't just relying on some hidden quirk of the C++ compiler. It means the underlying logic of the arena tree and the pure functions is fundamentally mathematically sound.
But, if you are a physical design engineer, staring at thousands of test outputs on a command line doesn't always tell you the whole story.
No, it doesn't.
I mean, you can have a test say a wire is 14 units long, but you need to know if that wire is actually snaking correctly or if it's routing itself completely off the silicon wafer.
Which is exactly why the developer had to build an entirely separate tool just to verify the visual geometry.
Yes, the clock tree visualizer. They built a tool that generates visual SVG image files, mapping the entire routing process.
It's a great tool.
Yeah, it uses a large red circle to represent the root source, so the metronome generating the clock signal.
Right.
It uses green circles to map out the leaf sinks, the final destinations, the transistors that actually need the signal. And it uses smaller blue circles for every single internal merge point we've been discussing today.
And what's fascinating here is how the visualizer exposes the behavioral differences between the math models in a way that numbers simply can't.
Oh, absolutely.
Yeah.
There's a specific comparison noted in the logs where they mapped an L-shaped layout of components. First, they ran the pure function using the linear model, the high school physics vacuum.
Right.
The visualizer drew the lines, and the text output showed a skew of 0.0. Perfect mathematical balance.
Because the linear math doesn't know anything about wire resistance.
Exactly. It's just looking at distance. Then they switched the pure function to the Elmore delay model. The visualizer recalculated.
And what happened?
Well, the blue merge points physically shifted their locations on the grid image, the wire snaking adapted, and the tool revealed a tiny realistic skew of zero point 0.6.
Wow.
Yeah. By visualizing the geometry, they could physically see the algorithm compensating for the friction of the metal.
And honestly, building that visualizer came with its own headaches.
Really? Like what?
Well, the logs mention having to fix a nested depth tracking bug just to get the images to generate correctly.
Oh, man.
It just underscores the reality of this kind of engineering. You spend half your time building the algorithm and the other half building the complex tools required to prove the algorithm isn't hallucinating.
It's a never-ending cycle. So what does this all mean for us, as we wrap up this deep dive?
Good question.
We watched a system evolve from a slow, chaotic library of scattered memory into a highly organized, contiguous arena. We saw the computation pulled out of the messy construction zone and turn into pure, observable blueprints.
Yeah, avoiding those side effects.
Exactly. And most importantly, we saw how embracing out of bounds, mathematically impossible data was the secret to creating those physical zigzags that perfectly synchronize the entire system.
I think it is a masterclass in how constraints actually breed architectural creativity. The rigid physical grid of the microchip didn't break the software's math.
Right.
Instead, the software adapted its math to navigate the physical constraints. It's brilliant.
It really is. And it's funny, we spend so much of our lives, whether we are talking about technology, our daily habits, or our teams at work, just trying to make every single individual component act as fast as humanly possible.
Well, constantly. We want the fastest processors, the fastest cars, the fastest workflows.
Right. But looking at the microscopic geometry of this chip, it achieves perfect systemic harmony by intentionally forcing its fastest signals to take a longer, slower, zigzagging path.
That is such a good point.
It really makes you wonder how much energy we waste in our own lives rushing to be fast, when what we really need is to design our systems to be in sync.